Hello everyone, my name is Connor Goodwin and I'm a math education major. Today I will be discussing the history of probability, gambling, and some interesting phenomena that involve probability in gambling. For this presentation, I will first begin by discussing how probability got started and the basic rules we know today were formed. Next, I will discuss a brief history of gambling, and lastly, I will talk about how some theories that have come out of the development of probability in gambling. First, let us discuss the history of probability and how this all got started. The idea of probability has been thought about for centuries, but no developments towards constructing a theory of probability have been found until 1654. In 1654, a French nobleman named Antoine Guimbaud loved games of chance, proposed a question to Pascal. Antoine, who is pictured at the top of the pictures, asked Pascal, who is the bottom left of the pictures, if he should bet money on the chance of rolling double sixes in 24 rolls of die. This led to Pascal and another great mathematician, Fermat, pictured in the bottom right, to discuss this problem through letters to one another. These letters were the first time that the principles of probability theory were formed. There are translations of these letters, but they are very hard to understand. While I tried to understand these letters, it seemed to me that the mathematicians were more interested in figuring out how to split the winnings of a game of chance, rather than the probability of rolling a double six. The next mathematician to make advances towards the official development of probability theory is Christian Huygens. Huygens was a teacher at Leibniz who we learned earlier about this semester. Huygens was the first to publish a book on probability called De Ratiocines in Lude Aliae, translated to On Reasoning in Games and Chances in 1657. In this book, he presented the idea of mathematical expectation, which we still use and learn about today, which is the same as the expected value of a certain scenario or variable. In the 18th century, there were three prominent mathematicians who made strides in the theory of probability. The first was Jacob Bernoulli, who is pictured on the top right. Bernoulli developed the law of averages, also known as the law of large numbers. The law of large numbers states that if you repeat a random experiment, such as tossing a coin or rolling a die, a very large number of times, your individual outcomes, when averaged, should be equal to the theoretical average. So essentially, if you were to flip a coin a large amount of times, the outcomes of heads to tails will get close to being 1/2 as you continue the experiment. The next mathematician who made developments in probability is Abraham de Morve. Morve published a book on probability known as the Doctrine of Chance. In this book, he indicates a method of calculating probabilities of events in play. The most significant contribution that came out of Morve was the approximation to the binomial distribution using the normal distribution in a large number of trials, which expanded on Bernoulli's law of large numbers. You will see Morve and the cover of the Doctrine of Chances in the bottom row of pictures. The last mathematician to make some contributions during the 18th century was Pierre Laplace. In 1812, Laplace introduced new probability techniques in his book Théorie analytique des probabilités. One of these ideas include finding the probabilities of compound events when the probabilities of their separate components are known. In this book, the ideas of probability were applied to more practical and scientific problems. Some of these include the theory of errors, actuarial mathematics, which is the science of calculating risk used in insurance and other professions now, and statistical mechanics. The last mathematician I will be talking about created the three probability axioms that we still use today. Kolmogorov was a Russian mathematician, and he was the one to develop these axioms. These three axioms were formed the basis of probability theory. The yellow picture at the bottom of the slide are these axioms' mathematical definitions, which may look more familiar to you. The first axiom states that the probability of every event is at least zero. So there is no such thing as a negative probability because it either does happen or never happens. The second axiom states the probability of an entire sample space is 100%, or 1. A sample space is a space that contains all the possible outcomes of a certain experiment or event. Therefore, since all outcomes are within the sample space, one of them has to happen. The last axiom Kolmogorov developed stated that if two events are disjoint, meaning either one happens or the other, then the probability that either of the events happening is the sum of the probabilities that each happens. An example of this would be like flipping a coin. This experiment is disjoint because you cannot get heads and tails at the same time, but the probability of getting heads is 50% and the probability of getting tails is 50%, so the probability of either happening is 100%. There were further developments in the theory of probability, but they involve a lot of complicated mathematics, so I will not be getting into that within this presentation. Next, let us discuss a brief history of gambling and how gambling was developed over the centuries. One of the first pieces of evidence of gambling was in 2300 BC in China. In China, researchers found tiles which were believed to be used for games of chance. They have reason to believe it was a lottery type of game based on historical writings, and another interesting thing they found was that the lottery funds were also used for civic purposes. Another piece of evidence of gambling in ancient times was found in ancient Rome around 500 BC. In ancient Rome, it was common to play dice games and wager in them. However, gambling eventually became illegal in ancient Rome. To bypass this law, the Roman citizens developed tokens to represent their wager, so when they were confronted or caught gambling, they could say they were giving away these tokens that had no value instead of actual money. This is the earliest known gambling chip, which we still use today in modern casinos. In the 9th century, playing cards were used in China. These cards were special because they were usually hand-painted, and they also bear literal relation to the playing cards we use today. The next advancement towards modern gambling was not found until the 1400s when baccarat was introduced. For those of you who do not know what baccarat is, it is still a game played in casinos today. In its simplest terms, each card has an assigned value, and whoever has the highest score each round wins. After baccarat, the earliest form of blackjack was found referenced in a book titled Don Quixote in 1601. Due to the book having Spanish origins, the game referenced in the book was called 21, which translates to 21 in Spanish. Other forms of the games has been found and referenced, but revolved around a different number besides 21, including 31 and 15. In 1638, the first gambling houses were formed. The gambling houses were formed so that gambling could be done during the chaos of carnival seasons or other environments, and they were also formed so the environment that they were gambling in was controlled. Next, in the 1800s, the origins of poker were pinned down to 17th century Persia in the French game called poker. The first recognizable form of poker, similar to the one played today, was found in New Orleans in 1829. The first gambling machines were created in 1891 in New York. They were first referred to as the one-armed bandit. These machines were developed by Messrs. Stitman and Pitt and consisted of 52 cards on a drum reel to make a type of poker game and resembled the picture towards the right. As you see on the right, there are 5 cards lined up within the screen. And as you pull the lever, the cards would move, and then you would get different cards each time. And depending on the combination of cards, you would win a prize. The machine to the far right is known as the Liberty Bell. And the Liberty Bell was preferred because winnings could be more regulated using it. Afterwards, gambling was developed to what we know today with electronic screens and casinos being nationwide and it being a fun pastime for people. Next, I will discuss some interesting beliefs, ideas, and a problem that have come out of gambling and probability. The first belief that I will be discussing is known as the gambler's fallacy. The gambler's fallacy is a psychological belief that has been found over the years when people participate in gambling. The first published account of this idea was by Laplace in 1820, who was discussed earlier with his contributions to the theory of probability. The professional definition of the gambler's fallacy is the belief in negative autocorrelation of non-autocorrelated random sequences. Essentially, people believe if one outcome happens, then the other outcomes have a higher probability of happening. An example of this would be a coin toss experiment. If you were to get heads on the first throw, the gambler's fallacy belief is that you expect tails to be more probable than heads on the second toss. This is not true because they are independent events. An independent event simply means that the outcome of an experiment before does not have an effect on the next outcome of the experiment. So when you flip a coin and get heads on the first throw, then the probability of getting heads or tails on the second throw is the same. This references the law of small numbers, which is the underlying belief that short random sequences should reflect the underlying probability used to generate them. This also could be thought about as the opposite belief of the law of large numbers. Another psychological theory based on the misconceptions of probability is known as hot hand. The hot hand theory is not as formal as the gambler's fallacy, but is still believed today. The hot hand belief is the belief that after a streak of correct guesses, then the probability of another correct guess is above 50%. The difference between this belief and the gambler's fallacy is the hot hand is based on wins and losses, not that a particular outcome is more probable. For example, gamblers who believe in the hot hand belief have a tendency to redeem winning lottery tickets for more tickets rather than cash because they believe another win is more probable after their previous win. Because of this, people can believe in both the gambler's fallacy and the hot hand belief, since the gambler's fallacy focuses on one event being more probable, while the hot hand belief focuses on a win or a correct guess. The next topic is a well-known problem based on the popular game show Let's Make a Deal. You may remember Let's Make a Deal. It was a game show where people would dress in ridiculous costumes with hopes of being called on and be able to win prizes by playing the game. A famous probability problem was researched during one of these games. The famous problem is referred to as the Monty Hall problem, and you may have heard of it. The problem was named after the original host of Let's Make a Deal in the 1960s, Monty Hall. The problem consists of 3 doors. 2 of the doors have quote-unquote goats behind them, while one has a car behind it. You can start out by picking one of the 3 doors. Once you pick your door, another door will be opened that does not contain the prize. So there are only 2 doors left, the one you picked and the one that was not open. Afterwards, you have the opportunity to switch doors or stay with the same door. The problem is, should you switch or should you stay with the door you originally chose? Pause the video and think about what you would do. Would you want to switch doors or would you want to stay with the same door? If you chose to switch, you have a higher probability of winning the car. It has been discovered that you should switch doors, because when you stay with the original door, then your probability is still at 1/3, while if you switch the door, your probability increases to 2/3. This occurs because when you make your first choice, you have a probability of 1/3 of choosing the correct door, because there are 3 doors, and when you pick one door, the probability is 1/3. While there is a 2/3 chance that you did not choose the correct door, because if you have a 1/3 chance of choosing the correct door, then there's a 2/3 chance that the other doors are correct. So when you switch the doors, you are picking a door that originally had a 2/3 chance of being the correct door, while the door you originally chose only had a 1/3 chance. Now, this does not include the idea that you could have chosen the correct door on your first try. However, in experiments done using this problem, they found that you have a higher probability of winning if you choose to switch doors within the problem. Now I will discuss a method that has been made illegal in casinos known as counting cards. To introduce this topic, you will watch a short video describing one method of counting cards.
So when I'm card counting, I'm playing perfect basic strategy, keeping accurate track of the running count, converting that running count into a true count based on the number of decks remaining, and then sizing my bet proportionally based on the true count. What makes blackjack different from all the other games is that it's based on dependent events, which means that the past actually affects the probability of what's going to happen next. Now, the card counting system that I recommend is called the high-low count system. We have the high cards, 10, Jack, Queen, King, and Ace, and these are good for the player. But they have a count value of -1 each because as high cards are depleted from the game, player advantage goes down. The next group of cards is the low cards, 2, 3, 4, 5, and 6, and these cards are good for the dealer. So naturally, these are going to each have a count value of +1, because as these low cards are depleted, that means there's fewer of them that can hurt you in future play. And the third and final group of cards is the neutral cards, 7, 8, and 9, and these cards don't have a count value at all because they don't favor the house or the player. If we were to look at these 3 cards, the count of these is -1. We have 2 high cards and 1 low card. For these 3 cards, they have a count of +2. So we have 2 low cards, which each have a count value +1, and the neutral card has no count value. Now, what most people would do once they learn the high-low count values is to adjust the count one by one. So, for example, they would think -1 +1 -1 +1 -1 -1 -1 +1. And so the net of all that work would be -2. So that required adjusting the count 8 times. But if you use a technique called meaningful pairs, you're going to reduce your workload and improve your speed dramatically. So looking at this first hand, we have a cancel, high-low, another high-low combination, another cancel, so no work required. Here we're going to have 2 high cards, so we're going to go -2. And once again, another cancel. And a neutral card doesn't mean anything with regard to the count. So using the pairs, we only have to adjust the count 1 time. Now once the hands are actually played out and players are hitting and doubling down, we will count them one at a time. So we're at -2, we take a hit, that brings us to -1, another hit, -2, -3, back to -2, and we end the round at -3. So The running count is very important. There's one more step. You need to convert that running count into what we call the true count. So this right here is about one deck of cards. The true count is simply the running count divided by the number of decks remaining, rounded to the nearest half deck. So for example, if you have a running count of +9 and there's 4.5 decks remaining, well, 9 over 4.5 gives you a true count of +2. And as true count increases, player advantage increases. So the general idea is to bet little or nothing when you don't have the advantage, and then bet proportionally more as your advantage increases. So as far as how we would size our bets, we would bet true count -1 betting units. So for example, if you had to have a betting unit of $25 and the true count is +2, well, 2 minus 1 is 1, so you should bet $25. So let's say the running count is +20. As you can see, we have one deck that has come out, meaning that there's 5 decks remaining. So that gives us a true count of 20 divided by 5 decks remaining. True count of +4. We're going to subtract 1 to get the optimal bet of 3 units. And let's use a betting unit of $100. So running count 20. So we're going to play this out. Now we have to play basic strategy as we're keeping track of the count. Now the count has moved down a bit to +17. So we have a +17 count divided by about 4.5 decks remaining. So we're still at about a true count of +4, so we can keep the same bet. Running count has increased to 23. So 23 with 4 decks remaining about gives us a true count of +6. So how much should we bet? Well, 5 units. So now you get a sense of everything that you have to do. You have to play perfect basic strategy, keep track of the running count, convert that into the proper true count based on the decks remaining, and then hopefully have enough leeway to be able to interact with other players and pay attention to what's going on.
Okay, so if you're anything like me, then that video just confused you. I had to watch the video a lot just to figure out what really was going on. So let me break it down for you. This is the high-low card counting system. Each card has assigned values, so the high cards add 1 to the total on the table and consist of 10, Jack, Queen, King, and Ace. The neutral cards make no change to the total on the table and consist of 7, 8, and 9. The last is the low cards, which add 1 and consist of 2, 3, 4, 5, and 6. Once you have the card values down, you want to add all of these values together to get the running count on the table. In the video, he mentions a technique called meaningful pairs, which essentially just means if you can recognize a high card and a low card together, you don't even really have to bother to add them together. This count provides you with an easily calculated probability for future cards. Essentially, the higher the count, the more likely you will get a higher card, and the lower the count, the less likely you will get a high card. And this is useful because low cards could hurt you in the future, because the point of the game is to get as close to 21 as you can, so the more low cards you get, then the likelier chance that you will bust instead of getting 21. Next is the true total, which is the running total divided by the number of decks remaining. You always want to round up if your true total is not perfect, and you also want to estimate the number of decks. It does not have to be perfect. As you see in the video, he did 4 and 4.5. He went from 4 to 4.5 with each round, so you can essentially just keep going down by a half with each round. And then the true count subtracted by 1 gets you the betting unit, which allows you to get a rough estimate of what you should bet based on the running count and all the cards on the table. The higher the drew count, then the higher the player advantage, meaning you'll be more likely to win more money. Now, I'm not sure if you could do this in a regular casino. I know I probably couldn't because that's just a lot going on. And one, I've never been in a casino, so I don't even know what it's like. But if you get caught, it's illegal, and apparently you can get kicked out for it. So I only recommend it if you can do it without looking like you're thinking really hard about it, because I feel like I would be the type of person to think really hard about it. But yeah, so good luck if you go to a casino and try this, and let me know how it goes. But that is all for my presentation on probability and gambling. I hope you found it interesting, because I sure did, and I didn't really know how much went into probability and gambling, and then I thought the theories were pretty cool to learn about. So thank you for watching.